So hello everybody, we are back again. So what we are doing, we are reviewing the key concept that we have covered in the last 3 weeks, and this is we are back after the break that we have taken. Now what we are reviewing here, we are reviewing the thermal plasma sources, radio frequency thermal plasma devices, their characteristics and features. So how the radio frequency plasma generated? What you are seeing here, that there are only few turns. You see that 1, 2, 3, 4, a coil is there, and that is coming out from here. What it is doing, it is passing a current through this coil, and the plasma is getting generated. And what is the frequency by which the current is changing? It is in the megahertz range. So what I'll do, I will tell you, there is an oscillator. Basically some of them are tube based and some of them are solid state device based nowadays. So basically what you need to create an oscillator. Here it is a coal pit kind of oscillator. Those who familiar with this electronics, how the coal pit oscillator works. So what we need, actually we need an oscillator which will drive the current at such high frequency. So this is the coil what I have shown here. So schematically over here, through this coil the current is passing once in clockwise direction, and next it is in anti-clockwise direction. So the current is switching like this and then like this. Now whenever there is a del B del T, so because the current is passing, so there is a magnetic field, and current is changing, so the magnetic field is changing. And because of this configuration, the magnetic field is axial, and that axial magnetic field is changing. So del B del T is in this direction. So curl of E equal to minus del B del T that you get from the Maxwell's equation. That tells you that the electric field so generated will be in the azimuthal direction. So if electric field is in azimuthal direction, then the current that electric field will drive will also be in the azimuthal direction, right, in this circular way. So the current one will be in this clockwise direction, and next time it will be in anti-clockwise direction within this tube, within this quartz tube, right? So when it does so, then the electrons are driven by that electric field, so they will collide with each other and generate the plasma. So that is the basically principle of generation of this radio frequency plasma. Now typical operating parameters of this radio frequency thermal plasma devices are like this. So you can see here that plasma gas is typically used argon. You can use many other gases as well. So here we are operating with 3 megahertz. This megahertz is the radio frequency range. Then the radio frequency voltage was around 4 kilovolt. Then what you are seeing here, the flow rate of the plasma gas, this is around 15 liter per minute. Then there is a seed gas flow which we are setting at 10 liter per minute, and there is a carrier gas. This gas is required to facilitate the process for which the device is designed. For example, if you are going for spheroidization of the particle, then this carrier gas will carry the particles to be spheroidized, or if it is for coating purpose, then this gas will carry the material that has to be coated. So this material are usually in the micron sized particles. They may be arbitrarily shaped, and when they enter into the plasma, they get molten and get sprayed over the substrate which you want to coat. Now interesting fact was that the temperature field within this plasma device usually shows a central dip. Why it is so? Because the electromagnetic field is entering from outside to inside, and they get attenuated by the conducting plasma as it moves inward direction. So because of the attenuation, it cannot hit with the same strength as it hits the peripheral region. So at the center, you always see a dip in the temperature. So sometimes if you are using a diameter of very small, then this dip may be not that significant. But if you are using a quite large diameter tube, then in the central region you can expect a dip in the temperature. So these temperatures we have measured using Abel inversion technique. Now comes the ECR plasma generation. This is a very important source for many applications. What you are seeing here, that this is the region where you have applied a magnetic field. So this is producing an axial magnetic field, and you are putting some microwave into this plasma region. Now what happens whenever a charged particle is there and you have applied a magnetic field? What it will do? It will start rotating around the magnetic field. Now when it is rotating, it is orbiting around the magnetic field. It is exactly like that. Now once it is in this direction, next time it rotates over in this direction, then next it comes in this direction, then it comes in this direction. Now what I want to emphasize, that direction of movement of the charged particle is changing. So one say in left, then right, so it is rotating like this. Okay. Now you imagine that when this particle is in this direction, if we apply an electric field in this direction, same direction, then the particle will be accelerated. Its energy will increase, and then what it will, it will start orbiting at a higher orbit of higher radius. So it moves like this. Then when it is here, you now apply an electric field in just opposite direction compared to what you applied in the previous case. So here the electric field was applied in this direction, now it is applied in this direction. So again it will be accelerated, and then it comes to an orbit of higher radius and reaches here. Now when it is here, then you apply another electric field, but it is now in the opposite direction. So what you are doing, you need to apply an alternating electric field matching with the frequency of that orbiting charged particle. Then you can impart energy to the charged particle. Now let us see what is the frequency of rotation of this charged particle. You see that here frequency is EB by m. So 2 pi is there because it is a linear frequency. Otherwise, if you go for angular frequency, it will be just EB by m. Now you see that it doesn't depend on the radius where it is orbiting. So once your electronic charge is fixed, one is your magnetic field is fixed, and mass of the particle is fixed, then frequency of rotation is fixed. So if you now apply an electric field of same frequency, here you see that it is in 10⁻⁹ Hertz, then what will happen? It will always accelerate the charged particle, and you can make the charged particle to raise to very high energy, and when they collide with each other, collide with other particles, they will produce the plasma. So for a here what we have seen, actually, if you are applying a 2.45 gigahertz, that is a standard commercial frequency, then what will be the value of the magnetic field that needs to be applied so that the electron cyclotron resonance takes place. So ECR is for electron cyclotron resonance, and here we are making an arrangement when we have an electric field frequency is fixed 2.45 gigahertz, then what should be the magnetic field? We have just made the calculation, and we see that is 875.6 Gauss. So when we apply this magnetic field, and this is the microwave frequency that we apply, then the plasma undergoes this electron cyclotron resonance, and what we get? A plasma that is created at the downstream here, and whatever processing that we want to do. For example, if you want to produce some radical and we want to deposit on a substrate, then we put some injection ring over here, and we inject the precursor over here, that get in touch with the plasma, they get ionized and they get deposited over the surface that we have put at the bottom. Sometimes the substrate needs to be heated, so there is some heating arrangement also at the bottom, but this is basically the principle for electron cyclotron resonance. The basic fact is that you need to have electric field in resonance with the rotational motion. So this cyclotron motion, you are resonating by applying a suitable magnetic field, so that the plasma receives energy from the microwave and it ionizes the particle whichever there in the container. Now comes the atmospheric pressure plasma jet. Here what we are using, electromagnetic induction principle. So what we are doing, this EMF that is created, that is proportional to the rate of change of magnetic flux. So here what you are seeing, there is a transformer, this is the primary, this is the secondary. Whenever you are changing a flux in the primary, a flux is induced in the secondary as well. Now what we are doing here, we are using a rectangular wave. Whenever there is a falling edge, this MOSFET goes off. The current suddenly changes. So that changes the magnetic flux all on a sudden, and that creates a very high voltage which causes breakdown of the gap between the cathode and the anode. There is a small gap in between, and when a very high voltage is applied between this gap, that is through the induction principle, then the region between these two is broken, and the plasma that is created hits the gas that is flowing through here, and a plasma jet comes out. Now when the plasma is formed here, it may be considered as a LCR circuit. L is formed by the secondary, and this is the capacitance of the plasma, and this is the resistive part of the plasma. So this together forms an closed loop oscillatory circuit. So whenever the discharge takes place at the falling edge of the input square wave signal, so the plasma is created and it starts oscillating because of the LCR nature of the circuit, and that helps the plasma to sustain quite a bit. And the plasma that is getting generated using that discharge, that usually contain frequencies which are not limited to the excitation frequency. Like this here, this is the 14 kilohertz. This is the frequency of that square wave by which we are inducing the plasma. But because of the oscillation that is present inside, because of the inherent nature of the plasma that has been created and the LCR circuit that has been formed, you see other frequencies are also present within the plasma created. So the important part is that the plasma is created very momentarily, and it is not a continuous plasma. So here you are getting the pulse, the plasma is formed, then again there is another pulse which is causing the plasma. So because it is created intermittently, the temperature of the plasma cannot go very high. Typically the gas temperature, you can see over here that this is somewhere around say 45-50 degrees centigrade, and the electron temperature can reach say beyond 2 eV. Here what you are seeing here, it is around here, it is around say more than 25,000 degree Kelvin, and you know that 11,600 is 1 eV, so it is more than 2 eV over here, and here it is around 1.5 eV kind of temperature you are seeing. So depending on the excitation frequency, you are seeing that you are able to control the temperature of the plasma that has been created. Similarly, the average power you can control, and the intensity of the plasma that has been generated, it goes like that, and you see that that is also having an impact of the frequency that has been used in generating the plasma. So the interesting thing of this kind of generated plasma is that they are having very high electron temperature, but gas temperature is very low, and that is bearable by the human cell. So this kind of plasma finds application in biomedical area because of the low gas temperature and high electron temperature. Whatever the electron mediated reaction that can happen there, and because of the low temperature, gas temperature, they are bearable by the biological cells. Now, physics wise, this kind of discharge exhibit many interesting discharge patterns within that. So apart from that, there are other cold plasma devices. Here this one is operating at 13.56 megahertz, and earlier one what you are seeing here, it is in the kilohertz regime. You see that the excitation frequency started from 15 kilohertz, 20 kilohertz, 25 kilohertz, and the whole range of frequency can extend up to say 800 kilohertz, but there anyway limited in a region which is less than 1 megahertz. But here in this case, what you are seeing here, this is 13.56 megahertz device. This is a cold plasma device. Again, this is this is a commercial frequency which is available in standard sources which are present in the market. So this device, again, there is a cathode and this is a anode, and it is water cooled because these are a bit higher power devices. The discharge takes place between the two, and the plasma jet comes out like this. So here you are seeing the actual device, the plasma is coming out over here, and here also you can use many types of gases like molecular gases here, nitrogen, oxygen, or argon. This radio frequency atmospheric pressure plasma jets are being now used in many applications, starting from your functionalization, then biomedical applications, then this noble material synthesis. So they are finding newer and newer applications in present days. Now the emission spectra, it goes like this. You can see when it is in argon, you can see even that emission of this atomic oxygen. So when this type of plasma are discharging in atmospheric air, some of the atmospheric oxygen molecules are broken and they can generate the atomic oxygens even. So even though it is a pure argon plasma, they can generate the atomic oxygen species through that kind of reactions. So here with distance, how the gas temperature varies and how the electron temperature varies, you are seeing over here. So similar to the kilohertz devices, these cold plasma devices are also applicable in the biomedical area because of the this electron temperature and the kind of gas temperature you are having. So this can produce various chemicals like this is hydrogen peroxide, nitrates, nitrites, and you see with time how the radicals concentration varies. Now there are dielectric barrier discharges. They are very simple. You take a glass tube, you put a central electrode over here and wrap a foil of conducting, say, copper foil, and then you connect an AC power supply, power source. So this also can be in kilohertz or in you can say megahertz range. There is no problem. Then what you get actually, you get a memory effect because of the dielectric that is in between this upper electrode and the central electrode. Here it is a glass that is serving as that. So afterglow particles like electrons, ions, metastables can persist for milliseconds or longer, influencing the next ignition. So that is the kind of memory effect. Then surface absorption and desorption. Active species can absorb onto the surface and later dissolve, altering the local chemistry. So this absorption and desorption plays a role in this kind of devices. Then thermal effects, heat retained in the gas or the surrounding material can reduce background voltage or modify the flow pattern. Then wall conditioning, previous discharge can chemically or physically alter the dielectric wall electrodes, changing the discharge characteristics over time, because that they can modify the properties of the dielectric that is in touch with the plasma. So all these are basically can be called as memory effect, which is significantly different from the direct discharge devices like the kilohertz device or the 13.56 megahertz RF device that I have shown you. Now, regarding the plasma temperature, you know that there are different kinds of equilibrium that exist inside the plasma. So there are kinetic equilibrium, then excitation equilibrium, then ionization equilibrium, radiation equilibrium. These things are there. So these things I have elaborately told in the classes. So the respective temperatures are T, the electron temperature, TH, the heavy species temperature, TEX, the excitation temperature, Ti the ionization temperature, and Trad is the radiation temperature. And corresponding, equation where this different temperatures fits in are shown over here. So these are basically, Maxwellian kind of distribution, and this is the, electronic excitation, and this is the ionization equation, and this is the radiation equation. Now, so each of them involves one temperature, and those temperatures are listed over here. Now, when we say the complete thermal equilibrium, we essentially say that the electron temperature, heavy species temperature, excitation temperature, ionization temperature, and radiation temperature, all of them are same. When you say that local thermodynamic equilibrium, apart from the radiation temperature, rest of the temperatures like T, TH, TEX, and Tion, all of them are same. When you say that partial local thermodynamic equilibrium, then this is anyway not valid, that radiation temperature is the same as electron temperature, heavy species temperature, excitation temperature, or ionization temperature. But what happens, that this T equal to TH equal to TX and Tn, this also doesn't hold for the lower lying electronic states. This relationship remains valid only for the upper lying states where the gap between the energy levels are less. So this kind of situation when some of the levels are not populated as per the Boltzmann distribution, but rest of the levels are populated according to the Boltzmann distribution. So those kind of scenario are referred as this partial local thermodynamic equilibrium. So you get the concept of CLT, LT, and PLT in this case. Then coming to the measurement of plasma temperature. So for non-invasive case, you use a spectrometer. Then the fiber collects the light from the plasma. Then it impinges on a collimating mirror. Therefrom to a grating disperses to different wavelengths, and those different wavelengths and their intensity falls on a CCD, and therefrom you get the intensity corresponding to different wavelengths. And this is the kind of intensity versus wavelength graph you get directly from the CCD based spectrometers, and there you get a relationship with intensity and the energy level, from which if you make a log of this quantity plotted as a function of the upper lying energy states where from the this transition is happening, then you see that this is a linear kind of plot with a slope of 1 by kBt. So if you are able to determine the slope, then you are able to find the temperature. But in this case, one thing, apart from this intensity, you need to know the wavelength, you need to know the degeneracy, you need to know the transition probability, and also you need to know the energy levels where from the transition is taking place. So for all this, you can go to standard data set like this one I have taken from this NIST data table. So there all the parameters are listed. You can get those parameters from there, and you can make a plot, Boltzmann plot, whatever log of that, and as a function of this upper energy level, and you get a straight line, and you find the slope of the straight line, and you get the temperature. And the existence of PLT can be vividly seen over here. You see that this 1 and 2, these two are the basically the lines that you are getting here. They are not in equilibrium with the as per the Boltzmann distribution. Okay, so rest of them are in equilibrium, so they are falling on the line, but these two levels are not populated as per the Boltzmann distribution. So the situation where from we have collected the data, so that stays in partial local thermodynamic equilibrium. So this is the kind of plot, and from the slope you just get the temperature, and here I stop. So we will meet you in the next review, and that will be probably the last review of the critical concepts that we'll be studying. So thank you so much for your attention, and I hope that you are enjoying the classes. Thank you very much.